starting from this paper by the German group, or from Weiss Kaiser. They were inspired more or less by the study of Weinberg in nucleon. To use unique chiral perturbation theory plus some non-perturbative methods. So there are many coupled channels. So this is an involved problem. Although you have only many interested in the K-bar-N scattering, you have to consider these SU3 related thresholds and states. They make all this decomposition in SU3 times SU3. So you have all these reducible representation. And all of them gives rise to resonances because they have they produce attractive kernels. So it's also a very rich study from the spectroscopic point of view. As I commented, the main motivation at that time to do this calculation was this planning for precise measurement of the shift due to strong interaction from the QED value and the fact that you have a width, because there are channels that are open once you consider strong interactions. So how to determine theoretically this shift? This paper appeared in 2005, the new measurement, yeah. And there was also some works by people from the Bonn University, Meson collaboration from Munich, or from Weiss, or José, etc., pointing out that there was a possible inconsistency between the new measurement by the via collaboration of this shift and width and more traditional SU3 scattering data. Indeed, in chiral dynamics 2003, Jurgasser indeed suggested us, really to consider this problem. He was also very interested in this kaonic hydrogen stuff. So we started to look at it from 2003. So in the first papers appeared in 2006, so it was long collaboration. So at that time there was also the promise of the Siddhartha collaboration with mutual improvement between Japanese and Italian people to even improve further the measurement of this energy of the lightest states. It was expected to arrive at a precision of just a few electron volts. However, this promised measurement, so accurate, it didn't come out. Last week appeared the measurement by Siddhartha, and the relative accurateness was similar to the one of the DIA, so it didn't improve as much as expected. Instead of reducing the background by 2 orders or 3 of magnitude, as they expected, they reduced it by 1 order of magnitude. So here, I will comment a bit how they do this kind of reduction. So this is basically one has to look at this y-axis. This is the background, which is huge. This is the problem. This is why these measurements are so difficult. So you see you have times 10 to the third power, and here you have 10 to the second. This is the last measurement from the last week. So this is the reduction of the background by 1 order of magnitude, which is not so, it's an improvement, but the real improvement is at the level of systematical error, because they manage, with this new Siddhartha collaboration, what they manage is to measure the X-ray in conjunction with the arrival of the kern. This can do because they have a very good timing resolution in the detectors. So this is how they can at least reduce this background by 1 order of magnitude with this Japanese collaboration together with people from Frascati. So this is the measurement. No? This is the first measurement in 1997, where they got right the sign, the measurement from Keck. This is the measurement in 2005, and this is the new measurement. So this is presumably, the last word. But since changes are, because they consider this coincidence, no, between X-rays and the arrival of the kern. So this is how this energy from the lowest state can be related to the scattering length. This is due to the Desert formula. Well, known Desert formula, you have this relationship, which was improved by taking into account isospin violating contributions, both from the electroweak part and also from QCD part, because of the difference in the light masses, worked out by this group from Bonn. So this is the relations. There are other interesting facts why to study K-bar-N scattering. For instance, there was a very well-known problem with the nature of the lambda 1405 coming from quark models. Also, we pointed out that it is very likely that indeed the lambda 1405 is a combination of two poles. Also, this has influence because possible condensation of strangens, for instance, in neutron stars, things like that, which indeed has been rolled out by new measurement from the upper limit in the mass of neutron stars. Also, the strangeness content of the proton was an issue. For that, you need to work out the scalar form factor, which is very sensitive to this kind of interactions. And also, there are also a lot of experiments going on activity in pion and kaon photoproduction. So this will be very, a very serious work here will be to join all the data from a strong interaction together with the data from kaon photoproduction in order to end with good knowledge on 55 minutes, a better knowledge on this physics, joining all the data, all the possible data. So I will just comment some idea. Why is it necessary to resum and go beyond perturbative ChPT when you go to SU3 ChPT? This is because you are involved with large masses. Simply is a kinematical reason. It was discussed by Weinberg, for instance, in his seminal papers on nuclear scattering. And the idea is quite simple. This is a unitarity diagram of kaon proton. Both of them has typical masses which are much larger than, for instance, the free momentum that is involved in the formation of the lightest resonances. Like here is the lambda 1405. In the neutron stuff, you have the deuteron. Well, here there is some denominators, some problem with the source. But it's simply because if you do the integration of Q0, or you think what you know from the Riemann-Stinger equation in quantum mechanics, you have the difference of energies between the initial state and the intermediate state. But here you have two heavy particles, so the difference in the energy is just due to the difference in kinetic energy. And the kinetic energy is much smaller than free momentum. So the denominator is huge. So whenever you have massive particles, if you are interested in processes where these massive particles appear in the external legs, you have to resum unitarity. Indeed, crossing symmetry is not so important. If you consider the same diagram, the cross one, in the U channel, you have to exchange k to minus k, you have to exchange the s variable by the u variable. So instead of having a difference of energies, you have the sum of the masses of the the masses of the kaon. So the relative between this unitarity and the cross loop is this ratio, 2mk divided by a free momentum, which is typically much more smaller than this quantity. So this could be something like 1 order of magnitude bigger, the unitarity diagram compared to the cross diagram. So this is why when one goes to this SU3 ChPT theory, one should really take very seriously to resum unitarity. So, and then what we do is to resum unitarity and then apply the chiral expansion for the interacting kernel. Well, this is how it's done, and okay, I will not go into the details. So this is at this time we went up to, in this paper we went up to next leading order, which is you have the order P, the Born terms and the Sigurd, plus the contact interactions. As I told, we wanted to go one order higher. This is what we did recently for nuclear scattering. There was this previous calculation. We repeated and correct one mistake here. And we are going. Finally, we want to go to SU3. So, there, one thing that is nice also in this SU3 study is that you have a lot of data. And it's a place that you can also study explicit breaking of chiral symmetry because you are sensitive to SU3 breaking and large masses. So it's a good ground to study explicit chiral symmetry breaking stuff. You have, as I told, several sources of data. I won't go into the details. The most recent ones, apart from this measurement of the kaonic hadronian stuff, correspond to reactions measured by crystal barrel collaboration, so we also implement. And, okay, these are the results we obtained. This is because at that time we include this data. This more recent data was not included in 2005. I included later. So I improved the. The main message is that we found two kinds of minima. A minima who agree with the new DR measurement and other minima who did not agree. Agree with the scattering data because there was this controversy on the scattering data and measurement of kaonic hydrogen. And so we found indeed two types of minima. One was compatible with this new measurement and the other not. So this is of this other data, we also find solution, including this last data from crystal ball, in agreement with dia, scattering, and all this new data. So one thing that was also interesting here is this controversy between these two kinds of solutions implies that there is nowadays still persists a factor of 2 of difference in the K- proton scattering length from one minimum to the other. Of course, if you believe nowadays the most recent measurement from this kaonic hydrogen, given during the last week by ChPT, then there will be more to this B plus scattering measurement, no? This value for the scattering length. So this is more or less the situation. This is the new measurement. This was the solution that agreed with this measurement plus the scattering data. The other kind of minima, this is the leading order, which was very close to ChPT in this, with the last measurement. However, this order P calculation has the problem that doesn't reproduce well one of the observables for scattering. So I think it will be worth, to still continue the effort and go to the one loop calculation and see, which are the solution who agree with this ChPT, and also to get values for the low energy constant in chiral perturbation theory. Just to end, as I told also, this is very rich area regarding spectroscopy. So you have a lot of Riemann sheets. In every of these Riemann sheets, because you have many thresholds, you have poles, and then it's a nice place where you can see how resonances cannot be well described simply by plate bigness, for instance, no? Because you change from one threshold to the other. Then you have to consider several poles for the same resonance. So these are, it came out that once you feed the data for scattering and for the dia, we reproduce all the resonances that are in the PDG up to 1800, indeed, quite high in energy. The lambda 1405, the 1670, and 1800 with isospin 0. And for isospin 1, more or less the same. I don't want to go into detail. So just to say that I kept a quite intense scientific collaboration with Simo around this year, but specifically since 2003. And I appreciate very much his help. He provided me good collaborations when I was starting in Murcia, which was really from the scratch. So there were not so many, so we thought that we were not far away each other. We were nearby, 2,050 kilometers. And I would also, for me, I am very, very thankful to him, no, because of this help and his trust in me. And things go on. So many times when we discuss, and I give reasons, and he listens, he gets his reason, we used to talk in Valencian, and he ends with something like potser. So he says quite quietly, maybe.